So hello everyone. This time we will be discussing the reduction oxidation reaction in our college chemistry laboratory or CHY 30.1. So this is the last topic for our balancing of chemical equation, the reduction oxidation reaction. So if you can see here, this is an apple. So why does cut fruit turn brown? You have probably noticed that the flesh of an apple turns brown after you remove the skin. The apple is still safe to eat, it just doesn't look as appetizing. So later on, we will discuss why is it when we cut off our fruits, they will turn brown. So identifying redox reactions, let us know first what are the two classes of chemical reactions. So there are two classes of chemical reactions. One is known as the oxidation-reduction reactions or reduction-oxidation reactions or redox reactions, in which electrons are transferred from one reacting species to another. And the other class includes all the other reactions in which no electron transfers occur. Now, many single replacement reaction, combination reactions, decomposition reactions, and combustion reaction are known to be redox reactions. In this case, our example here, potassium metal reacts violently with water to produce hydrogen gas and potassium hydroxide. So our potassium metal belongs to the group 1 alkali metals. This is a very reactive solid that when allowed to react with water can produce hydrogen gas and potassium hydroxide. So this is an example of a redox reaction. Now many single replacement reaction, combination reactions, decomposition reactions, and combustion reactions are also known to be redox reactions. In this case, our zinc metal reacts vigorously with hydrochloric acid to produce hydrogen gas and zinc chloride. So example of reactions that are not redox reactions include double displacement or double replacement reactions and acid-base reactions. So some fruits, including apples, turn brown when you cut them. So what do you think is happening on the surface of the fruit that causes it to brown? The answer here is that the oxygen in air reacts with the chemicals on the surface of the cut fruit. Therefore, the oxygen oxidizes the chemicals in the fruit, causing a redox reaction and therefore a color change. That's why we have this brown color when we cut the fruit and allowed it to be exposed to air. There is an oxidation going on by the oxygen that reacts on the surface of the cut apple. So now, in this oxidation reduction reactions, remember that there is a transfer of electrons. So there is a loss of electrons and there is a gain of electrons. So we should know when is the substance oxidized and when is the substance reduced. So we say the substance is oxidized once it loses electron. We say that the substance is reduced once it gains electrons. Okay? Oxidized once it loses electrons and reduced once it gains electrons. Now, in order for us to keep track about the transfer of electrons, it is necessary for us to know the oxidation numbers. So when we say the oxidation number for an ion is the charge on that ion. The oxidation number of an atom is the hypothetical charge that an atom would have if it was an ion. So the oxidation numbers are assigned by a series of rules. So if the atom is in its elemental form, the oxidation number is 0, like Cl2, H2, P4, or even O2. For monoatomic ion, the charge on that ion is the oxidation state. Example here are our potassium, K+. What is its charge? If its charge is positive 1, since it belongs to the alkali metal, therefore its oxidation number is also +1. In the case of barium, its charge is 2+, since it belongs to the group 2 alkaline earth metals. Therefore, its oxidation number is also 2+. So those are examples for monoatomic ion. Now, in the case of non-metal usually have negative oxidation numbers. In the case of oxygen, oxidation number of oxygen is usually -2. For the peroxide ion, take note that the peroxide is represented by O22-. This has an oxygen with an oxidation number of -1. Oxidation number of hydrogen is positive when bonded to nonmetals and -1 when bonded to metals. And take note the oxidation number of fluorine is -1. The sum of the oxidation numbers for the atom is the charge on the molecule. And when the molecule is neutral, the charge is 0. So these are examples of oxidation of metals by acids and salts. So metals are oxidized by acids to form salts. In this example, we have our magnesium that is oxidized by our hydrochloric acid to form magnesium chloride and hydrogen gas. During the reaction, the 2H plus is reduced to H2, and the metals can be oxidized by the other salts. Notice that the iron is oxidized to Fe2 plus and the nickel is reduced to nickel, which has a charge of equal to 0. So take note, when our element is oxidized, it gains an additional oxidation number, charge on the oxidation number. While when the element is reduced, it loses, or its oxidation number decreases. So for the activity series, some metals are easily oxidized whereas others are not. Activity series is a list of metals arranged in decreasing ease of the oxidation. The higher the metal on the activity series, the more active that metal is. Any metal can be oxidized by the ions of elements below it. So this is an example of the activity series. So the metal here in the upper portion are the one that is very reactive for the oxidation, while in the lower portion are lesser reactive with the oxidation. Take note, when we are dealing oxidation reaction, this is the half reaction for the oxidation reaction. In this case, in the left side or the reactant side, our lithium here has a 0 charge. Take note that during oxidation reaction, there is an increase of oxidation number. And looking at that metal, which is the lithium on the product side, it has an oxidation number here that is equal to +1. So it gains 1 electron, or no, it doesn't gain 1 electron, but its oxidation number increases. So we place that additional electron here that is being lost by the oxidized substance. Okay, we place the additional electron in the product side that is being lost by the oxidized substance. So just remember that when we have an oxidation reaction, we place the electrons in the right portion or the product portion, but when we have a reduction reaction, we place the electrons in the left portion. Okay, so in the oxidation reaction, there is an increase in oxidation number, but in the reduction reaction, there is a decrease in oxidation number. So these are a summary of rules in assigning oxidation number. Do not forget that for an atom in elemental form, the oxidation number is 0. For monoatomic ion, what is the ion charge is equal to the oxidation number. And the sum of oxidation numbers is equal to the charge of the formula or the molecule. So for group 1A, the oxidation number is +1 in all compounds. So here is our group 1A in our periodic table, that are lithium, sodium, potassium, rubidium, cesium, and francium. For group 2A, which are beryllium, magnesium, calcium, strontium, and barium, and radon, that is equal to +2 oxidation number. They have +2 oxidation number. For hydrogen, it has a +1 charge when it is combined with non-metals, while it has a -1 charge when it is combined with metals and boron. For fluorine, it has a -1 charge in all compounds. For oxygen, has a -1 charge in peroxides, while it has a -2 in all other compounds. Remember the oxidation number of your fluorine. Well, for group 7A, which are our fluorine, chlorine, bromine, iodine, fluorine, chlorine, bromine, and iodine, we have a -1 charge here when it is combined with metals and non-metals except for oxygens and other halogens in its lower group. Okay, so now let us have an activity here. So this time we have to determine the oxidation number of each element in this species using these rules for assigning oxidation number. Again, you have to be very well versed in determining the oxidation number in order for you to keep track the transfer of electrons during the redox reactions. So in this case, we have zinc chloride. The formula of zinc chloride is ZnCl2. So if we are going to do a check here in the oxidation number, remember that chlorine is a halogen. So for halogens that are under group 7A, again, they have -1 in combination with metals. So chlorine has a -1 oxidation number times 2, because there are 2 chlorines here, that is equal to -2. So since the molecule is neutral, its overall charge is equal to 0, the charge of our zinc should be +2 in order to have a neutral Cl2 or zinc chloride molecule. So that is how you determine the oxidation number. In case that you do not know the oxidation number of other element, you should first determine what is the known oxidation number in that compound and then calculate the total charge from that oxidation number, and then determine the overall charge of your molecule. And then based on the overall charge of your molecule, you decide what should be the oxidation number of the remaining element that has not yet record for the oxidation number in that compound. Okay, so now let's go to letter B, which is sulfur trioxide. So the formula of our sulfur trioxide is SO3. Now our oxygen has a again, when it is bound with all other compounds except fluorine, it has a -2 charge. So it is first determined. It has a -2 oxidation number, and then our oxygen is equal to 3. So what should be the oxidation number of the oxygen? That is equal to -6. That is the total oxidation number for all oxygens. For the sulfur, since our molecule is neutral, the charge of the sulfur should be +6 in order to get a neutral SO3. So the charge in this case for oxygen, the oxidation number is equal to -2, while the oxidation number of sulfur is equal to +6. Okay, oxidation number of oxygen is equal to -2, while the oxidation number of sulfur is equal to -6. So in the case of nitric acid, we have a formula here which is equal to HNO3. Now, if we are going to check the oxidation number of oxygen, it is -2 in all other compounds. So you determine the oxidation number of your oxygen first, especially when all others are not yet known. Okay, so or it has an oxygen in the compound formula unit, so you determine the oxidation number of oxygen first. Oxidation number of oxygen is -2 in this molecule, since we have 3 that will be multiplied to 3, which is equal to -6. So excuse me, we have to total the oxidation number here of our oxygen in our HNO3. I have to delete. So we have oxygen in this is the case of HNO3. We have oxygen, which is -2, since it has 3, so -6. We have hydrogen that is bonded to a non-metal. Take note, when it is bonded to a non-metal, its charge is +1. We only have one hydrogen, so the overall charge is +1. So in this case, we have -6 plus 1 is equal to -5. Our molecule is neutral, so we need, since -6 plus 1 is -5, so we need a +5 charge in order to have a neutral molecule. So in summary, we have the oxidation number of oxygen here, which is equal to -2. The oxidation number of hydrogen is equal to +1, while the oxidation number of nitrogen is equal to +5. If we are going to get the sum of those charges that is equal to 0, that just means that we have a neutral nitric acid here. In the case for dichromate ion, the formula here is Cr2O7 2-. Again, get the oxidation number of your oxygen first. That is, your oxygen has a -2 charge times 7, so that is equal to -14. Take note that our chromium, we have 2 chromium. So in the case of our chromium, we have 2 chromium times, since we have a -2 charge here, we should have an equal to +12 in order to get the -2 overall charge here. So in the case of +12 charge, overall charge for chromium, take note that we have 2 chromium here. So we should have +6 times 2 is equal to +12. So -14 plus +12, that is equal to a -2 overall charge for the dichromate ion. So in this case, the oxidation number of our oxygen is -2 here. For the dichromate ion, the oxidation number of our oxygen is equal to -2, while the oxidation number of your chromium is equal to +6. Take note that it says a -2 overall charge here. Again, if you are going to look for the oxidation number, you assign the oxidation number first of the oxygen, followed by the known oxidation number for any other elements. So, identifying redox reactions. This is an example during an electrical storm in which oxygen molecules and nitrogen molecules are in air and react to form nitrogen monoxide. So how can you tell if it is a redox reaction? Well, you should keep track about its individual oxidation number. So in this case, we have a 0 oxidation number for our nitrogen since it is in elemental form, while our oxygen has a 0 oxidation number since it is in elemental form. Now we have a nitrogen monoxide product. In this case, take note, when oxygen is partnered with any other element, its oxidation number is -2. Well, for the nitrogen, it should have a +2 oxidation number in order to neutralize this, in order to have a neutral charge in this nitrogen monoxide compound. So in this case, the oxidation of nitrogen increases from 0 to 2. So when it is the oxidation number increase, that means that that substance is being oxidized. Okay? When the oxidation number, in this case of oxygen, decreases from 0 to -2. So once the oxidation number decreases, the substance is said to be reduced. Okay? So again, an increase in oxidation number means the substance is oxidized, while a decrease in oxidation number just means that the substance is reduced. So the reaction between nitrogen and oxygen to form nitrogen monoxide is a redox reaction because there is a transfer of electrons. There is a change in the oxidation number from the elements in the reactants going to the product side. So another example of redox reaction is a reaction between the permanganate and bromide ion to produce manganese ion and bromine ion. Okay, so this is a violet permanganate ion combined with a bromide ion, which is colorless, to produce the manganese 3 ion, which is colorless, and a bromine, which is brown in color. So take note that in this case, we have bromine here that is negative 1 yung ang charge. Then we have bromine here which is elemental, so it has 0 charge. In this case, take note that we have oxygen that is binded to manganese, so negative 2 oxygen times 4, that is equal to negative 8. We have a negative 1 charge for the overall charge of our molecule, so the charge of the manganese should be positive 7. So here, positive 7 ang ato ang manganese, while negative 1 ang ato ang bromine in the product side. So take note, if we are going to assign the oxidized substance and reduced substance, remember when there is an increase in oxidation number, the substance is said to be oxidized. When there is a decrease in oxidation number, the substance is said to be reduced. So in this case, our manganese has a positive 7 charge in product going to a positive 2 charge in reactant. Our bromine has a negative 1 charge in our reactant going to 0 charge in our product. Take note that our manganese has a lower oxidation number when it went to its product side. Therefore, the substance is said to be reduced. While on the other hand, our bromine from negative 1 increases its oxidation number to 0. Okay, so that means that the substance is said to be oxidized. Okay, so this is an example of the activity series of metal. Take note that when we have an oxidation reaction, we have electrons situated at the right portion, but when we have our reduction reaction, we have electrons situated at the reactant portion. So this is a summary of redox terminology for oxidation, for reduction. So in oxidation, one reactant loses electrons. So in this case, if we have zinc that reacts with H plus to form zinc 2 plus and H2, take note that zinc is elemental in form here, then it gains a positive 2 charge here. H plus has positive 1 charge here. In this case, it is elemental in form, that is equal to 0 na din yung charge. Take note that the substance which increases its oxidation number, in this case the zinc, so it is under the oxidation reaction, while the substance that reduces its oxidation number, in this case the H plus, undergoes the reduction reaction. So one reactant loses electrons, in this case the zinc loses electrons. Therefore, when the substance loses electrons, it is oxidized. Therefore, it is a reducing agent once it is oxidized. So zinc is the reducing agent and becomes oxidized. So there is an increase again of the oxidation number. The oxidation number of zinc increases from 0 to positive 2. On the other hand, the reduction reaction gains electrons. So the hydrogen gains electrons here. Oxidizing agent is reduced. Okay, so the hydrogen ion is the oxidizing agent and becomes reduced, and the oxidation number decreases. Therefore, the oxidation number of H decreases from positive 1 to 0. It is also important for you to just remember the Leora and the Geroa. When you say Leora, that is just loss of electrons, means that the substance is oxidized. Therefore, it is a reducing agent. Okay, do not forget, when a substance loses electrons, meaning there is an increase in oxidation number, it is oxidized. When the substance is oxidized, that is the substance that is the reducing agent. On the other hand, When a substance gains electrons, the substance is said to be reduced. Electrons. The substance is said to be reduced. When the substance is said to be reduced, that substance is called the oxidizing agent. So just don't forget the Leora and Geroa. Don't forget that in oxidation reaction, there is an increase in oxidation number. In reduction reaction, there is a decrease in oxidation number. Do not forget the Leora and Geroa to assign the reducing agent and oxidizing agent, and remember the gains of electrons and the loss of electrons. So in this case, we have to identify if it is a redox reaction. So again, we just have to keep track of our electrons. In this case, Cl2 is 0 since it is in elemental form. Our sodium here is positive 1. So it combines with bromine, which is equal to negative 1. Our chlorine here is negative 1, while our sodium here is positive 1. Our bromine here is equal to 0. Take note that sodium charge is just the same, so it is not included. So we erase it. So what is left now is our chlorine and our bromine. We have to check which is the one oxidized and which is the one being reduced. So again, when you have an increase in oxidation number, the substance is said to be oxidized. When you have a decrease in oxidation number, the substance is said to be reduced. In this case, we have chlorine that is equal to 0 going to negative 1. Take note that its charge in its oxidation number is decreasing. Therefore, our chlorine is being reduced. So the substance reduced here is our chlorine, while the substance being oxidized is our bromine, because from negative 1, the oxidation number increases to 0. So once you say when the substance is reduced and substance is oxidized, remember the Leora and the Geroa. Take note that the substance is reduced, therefore this is the oxidizing agent, because when the substance is reduced, that is the oxidizing agent, OA. Bromine is oxidized here, therefore this is the reducing agent. And this one loses electron. And this one gains electron. When the substance is oxidized, there is an increase in oxidation number, and when a substance is reduced, there is a decrease in oxidation number. Do not forget those steps. So if changes in oxidation number occur, a redox reaction is going on. The element whose oxidation number increases is oxidized and is the reducing agent. The element whose oxidation number decreases is the reduced and is the oxidizing agent. So we also already answered that one. So this is a technique in balancing redox reaction, the half reaction method. So this method divides the overall redox reaction into oxidation and reduction half reactions. So each reaction is balanced for mass and atoms charge. One or both are multiplied by some integer to make the number of electrons gained and lost equal. Don't forget that the number of electrons gained should be equal to the number of electrons lost. Now the half reactions are then recombined to give the balanced redox reaction, and its advantages for the half reaction method is the separation of half reactions reflect the actual physical separations in electrochemical cells. The half reactions are easier to balance, especially if they involve acid and base, and this is usually necessary to assign oxidation numbers to those species not undergoing change. So in this case, we have the reaction for a dichromate ion and a iodine. So now, let's divide the reactions into half reactions. So we have to determine which one is oxidized and which one is reduced. So determine the oxidation number for the species undergoing reaction. So for the chromium, you have a positive 6 here since we have oxygen charges equal to negative 2 times 7, that is equal to negative 14. So we should have a positive 12 charge in our chromium. Since it has 2, so we should have a positive 6 charge in each of our chromium times 2, which is equal to 12. So the overall charge of the molecular formula is equal to negative 2. Now, in this case, your iodine has a charge of negative 1. Your chromium in the product has a charge of positive 3. And your iodine has a charge of 0 in the product since it is in elemental form. Now, when you get the half reaction from Cr2O7 to minus to Cr3 plus, you know that the chromium is going from positive 6 to positive 3, meaning its oxidation number decreases. Therefore, it is a reduced substance. While on the other hand, the iodine from negative 1 to 0 has an increasing oxidation number. So you already know here who is oxidized and who is reduced. The iodine here is the one being oxidized, while the chromium is the one being reduced. Next, when you determine which one is the reduction reaction and which one is undergoing the oxidation reaction, you have to balance the atoms and charges in each half reaction. So let's start with dichromate. So take note that you have 2 chromium in the reactant portion and you have a 1 chromium in the product portion. So you have to multiply the product portion with 2, which is the stoichiometric coefficient. So in the case that we don't have a oxygen here in the product side, so we can have, or we can add a total of water molecules which is equal to the total number of your oxygen in the other side. In this case, we have 7 oxygen in the reactant side. So we can add 7 water molecules to the product side or to the other side in order to compensate with the oxygen element in case if there is none. So we add 7 oxygen, and in order to balance the hydrogen, we add 7 times 2, which is equal to 14 H plus. Okay, in order to balance the elements in that half reaction. So if we continue, so the net charge plus here is equal to positive 12, since we have a positive 6 charge in each chromium, and we have a charge here of the chromium which is equal to positive 6 since we have 2 chromium times positive 3, which is equal to positive 6. So we add 6 electrons to the left. Okay, so this is the 6 electrons to the left, since we add to the left since this is a reduction reaction. Okay, so 6 electrons are being gained in order to have this 3 plus charge of this 2 chromium in the product side. Okay, we add the electrons gained for the reduction reaction in the left, and we have to add the electrons lost in the oxidation reaction in the right portion of our chemical equation later on. So now we have our iodine, the balancing of our iodine. We already know that. So in the case of iodine, from negative 1 to 0, this is the oxidized form. In order to balance it, we just place a 2 stoichiometric coefficient into the reactant side. And since this is oxidized, we have to sum up that there are 2 electrons, or there are 2 iodine, and each iodine has a negative 1 charge in the reactant side. So since it undergoes an oxidation reaction, we have to account that there are a total of 2 electrons that is lost in the reaction, and the electrons lost are placed in the product side, the total number of electrons lost. So that is equal to 2 electrons, since there are 2 -1 charges of this iodine here. So take note that chromium is the oxidizing agent while iodine is the reducing agent. So now we have to multiply each half reaction by an integer if necessary. Take note that our iodine here has a positive 2 electron, while this one is equal to it has 6 electrons, and based on our rule, the number of electrons lost should be equal to the number of electrons gained. So we have to multiply this one by 3 in order to have a total of 6 electrons that is in the oxidized portion, that is equal to the reduction portion. Okay, so if we are going to multiply it by 3, we have 6 iodine minus in the reactant plus 3 I2 plus 6 electrons. So that is the total. If we are going to get the total of this reaction, take note that our electrons here lost and gained will cancel. So we are going to copy the 14H plus, this Cr2O7 to minus, the 6 iodine, the 2 chromium, the 3 iodine, and the 7H2O. Take note we still have H+. We have to undergo this via a neutralization reaction. So do a final check on atoms and charges. Then in order to balance the H plus ions, we have to add the OH minus ions. So in this case, since we have 14H plus, we have to add 14 OH minus in the left and 14 OH minus in the right portion. So in order to have 14 OH minus in the left, so that means that we have a 14 total of water here, because H plus plus OH minus is equal to 14 H2O. Now in this case, you have 7 H2O plus 14 OH minus. Okay, so in this case, the total here is 14 H2O plus Cr2O7 2 minus plus 6I to Cr3 plus 3I2 plus 7 H2O plus 14 OH minus. So in this reaction, we have to reconcile the water molecules. So the total number in the reactant should be subtracted to the total number of products. Take note that you have the higher number of water molecules in the reactant, so 14 minus 7, so this is lost. Therefore, there are only 7 water molecules left in this reactant portion. So here are the 7 water molecules left. And then you still have the 14 OH minus. So we have to do the final checks on atoms and charges. And this is the redox reactions between a dichromate ion and the iodide ion. So we have a color brown solution later on after the oxidation. So the last example we have is the permanganate ion, a strong oxidizing agent, and its deep purple color makes useful as an indicator in redox titration. This reacts with the basic solution of the oxalate to form carbonate ion and solid manganese dioxide. Now we have to balance the reaction with the carbonate ion and the solid manganese dioxide in basic solution. So we just have to use our previous idea. We have to determine which one is reduced and which one is oxidized. So in this case, so we have to assign the charges for manganese, that is equal to +7 to +4. There's a decrease in oxidation number, therefore it is reduced. In the case of oxalate, you have a +3 to +4, so there is a increase in oxidation number. So the oxalate is the carbon dioxide is the one being oxidized. Okay. So in order to balance the equation here from our MnO4 minus and MnO2, take note that we have a single manganese on both sides. However, we have a lacking 2 oxygen in the product side since we have 4 oxygens in the reactant side. We just have to compensate it with water, which is equal to 2. And this 2H here, which is 2 times 2, it's equal to 4 hydrogens. We just have to add it onto the other side of the reaction. Okay, so we have to add 4H plus here. Now on the other hand, we have an oxalate which is C2O4 2 minus, and we have to balance the number of carbons into the product side. Take note that we have 2 carbons in the reactant side, so we have to place a stoichiometric coefficient which is equal to 2 and the carbonate molecule into the product side. And then in order for us to compensate with the number of oxygen atoms into the product side, take note that we have 2 times 3, we have 6 oxygen atoms here. When we don't add yet the oxygen atoms, we only have 4, so we lack 2. So in order to compensate with the oxygen atoms, we have to add the lacking oxygen here via the addition of water. Now we have positive 2H2 on the left side, and in order to compensate the hydrogen, we just have to add the total number of hydrogens from the water molecule here, which is equal to 4H plus. So take note that there is a 3 electrons that is being gained by this MnO4 minus going to MnO2, and there are 2 electrons that is being lost by this oxalate, the carbon in the oxalate here. So in order to have a balanced reaction here, we have to make the total of number of electrons into both sides to equal. So we have to multiply with a specific number. Now, this is the result if we are going to make the number of electrons gained and lost in the product and reactant side equal. So we then get the total reaction, which is then we have makancel naman itong 6 electrons in the product and reactant side. So we have 8H plus 2MnO4 plus 6 electrons going to 2MnO2. We have to get the total, which is equal to, then take note that your 8H plus and 12H plus here, we just have to get the difference of this. Therefore, mawala siya. We have here, the remaining of this will equal to 4H plus. Since 12 minus 8, that is just equal to 4H plus. So the total reaction here should be 2MnO2, down lang ni, 3 C2O4 minus, and then 2H2O going to 2MnO2, going to 6CO3, and going to 4H plus. In order to balance the acids or the H plus, we just have to add the OH minus in both sides. So here plus OH minus here, which is equal to 4, and plus 4OH minus here. So in this case, we have a total here, which is we have 2H2O here. Take note that if we have to add 4OH here, that is equal to 4H plus 4H, that is equal to 4H2O, and we have H2O, and we have 4OH minus here. Okay, so Y2H2O 4H plus, and we have 4OH minus. So 4H plus and 4OH minus, that is not equal to 4H2O, but instead 2H2O, since we have here 4H plus 4OH minus, 4H plus 4 hydrogens in 4OH minus, that is equal to 8. However, so that is equal to 4 rather, sorry. This is equal to 4H2O. However, take note, we have 2H2O here in our reactant side. So 2H2O minus 4H2O, that is equal to 2H2O remaining. So this is the overall balanced redox reaction for the reaction between manganese and the C2O4 2 minus, which is oxalate in the oxidized form. Okay, so this is the balanced reaction of that problem.